The Lockheed factory at Burbank in 1939 was a place of contradictions. Half experimental laboratory, half production line. Outside, California sunshine lit the San Fernando Valley. Inside, the hangars smelled of oil, aluminum dust, and new invention. The project that absorbed everyone's attention carried the internal designation Model 22. The Army called it the XP-38, a radical twin-boom interceptor designed by a team of engineers scarcely over 30. At its head was Clarence L. Kelly Johnson, brilliant, impatient, and already convinced that air warfare was about to change forever. Johnson's Lightning was revolutionary in form and purpose. Its twin engines promised both speed and reliability. Its tricycle landing gear and streamlined booms gave it an unmistakable silhouette. But its most daring feature was the concentration of all its guns in the nose. 4.50 caliber Browning machine guns clustered around a 20mm Hispano cannon. In theory, this arrangement eliminated the convergence problems of wing-mounted guns. Every bullet and shell would travel straight ahead along the pilot's line of sight. In practice, it created new problems that no one yet knew how to solve. The cannon installation was heavy, its recoil violent, and the synchronization between the weapons inconsistent. The Hispano's feed system jammed under G-load. The recoil springs deformed after repeated firing. Lockheed's armament department, accustomed to the smooth operation of Brownings, found itself dealing with a weapon originally built to British specifications. The company needed help, someone who understood not aircraft but guns. In the spring of 1940, that help arrived in the form of Edward T. Ed Layton, a civilian mechanical engineer from Springfield, Massachusetts. Layton had spent a decade designing automatic feed mechanisms for the armaments division of Savage Arms before the war. When the Army Ordnance Department asked Lockheed for outside assistance, his name appeared on a short list of men who combined mechanical intuition with a talent for improvisation. He arrived at Burbank carrying a single briefcase and a set of calipers polished from use. Layton was not a pilot and had never worked on an airplane. He approached the P-38's gun bay like a machinist approaching a stubborn press. The first time he saw the Lightning's nose section, he was astonished at how little space existed between the gun breeches, the oxygen tanks, and the radio equipment. "You've built a piano and asked it to play artillery," he quipped to Johnson, earning a grin from the famously terse designer. What struck Layton immediately was the misalignment of the cannon's recoil line with the aircraft's center axis. Each time the 20mm fired, the entire nose twisted slightly, producing vibration that disturbed the Browning mounts and threw off accuracy. Lockheed's engineers had assumed the effect negligible. Layton measured it with dial indicators and found a deflection of nearly a quarter inch. His solution was elegant in its simplicity. A floating cradle mount that allowed the cannon to recoil straight back on hydraulic rails, absorbing shock without transmitting it to the surrounding frame. The idea was unconventional and, at first, unpopular. Hydraulic mounts added weight and required fluid lines that could leak under altitude pressure. Johnson listened impatiently as Layton sketched diagrams on the back of a blueprint. But the logic was undeniable. "Let me build a test rig," Layton said. "Give me 2 weeks and one good machinist." He got both. In a side hangar at Burbank, Layton and his assistant constructed a steel cradle lined with neoprene pads and fitted with small hydraulic dampers scavenged from landing gear shock struts. They bolted a surplus Hispano cannon into the frame and fired it remotely. The weapon jumped, roared, and settled back with a smoothness none of the Lockheed team had seen before. High-speed cameras confirmed it. The recoil pulse was reduced by nearly 60%. The test data convinced Johnson, who signed an authorization for limited installation on the next prototype. The modification changed the character of the Lightning's fire. With the hydraulic cradle, the cannon could sustain longer bursts without jamming or shaking the nose structure apart. It also allowed precise harmonization of the machine guns around it, since the entire battery now remained rigidly aligned during firing. Test pilots reported tighter shot patterns and improved accuracy at long range. "It hits like a single hammer instead of 4 hammers out of step," one pilot noted in his report. By the time the first production P-38's rolled out for the Army Air Corps, Layton's design had been refined and standardized. The civilian engineer received no publicity. His contribution buried in technical bulletins under the heading Armament Vibration Control System. But among the mechanics at Lockheed Field, his name became shorthand for ingenuity. "Give it the Layton treatment," they said whenever a piece of equipment refused to cooperate. The Lightning entered service in 1941, sleek and menacing, yet still evolving. Early combat over North Africa and the Aleutians exposed new flaws: cold weather malfunctions, oxygen leaks, and gun jams caused by frozen lubricants. Each problem returned to the factory for analysis, and Layton was often the one who devised the fix. He experimented with silicone dampers that maintained viscosity at sub-zero temperatures and redesigned the ammunition feed chutes to prevent belt flutter at high altitude. The cumulative effect was a machine whose nose battery could deliver an unbroken storm of lead and explosive at more than 1,000 rounds per minute. To the pilots who flew the Lightning into combat, the transformation was tangible. Major Richard I Bong, who would become America's top ace, described the sensation of firing the improved guns as like pointing a finger of God. When all 5 barrels spoke at once, the aircraft barely shuddered, a testament to the unseen engineer who had tamed the recoil that once threatened to shake it apart. Layton remained a civilian throughout the war. He wore no uniform, drew his pay from Lockheed, and spent most of his time moving between test sites in California and armament ranges in Florida. His correspondence with the Army Air Forces reads today like a chronicle of incremental innovation: requests for stronger alloys, notes on hydraulic seals, sketches of pressure valves. Yet within those details lay the quiet revolution that made the P-38's concentrated fire one of the deadliest weapons in the Allied arsenal. By late 1942, production P-38GS and H models incorporated a refined version of the hydraulic cradle and improved gun harmonization geometry derived from Layton's measurements. Combat results confirmed its effectiveness. Japanese and German pilots alike learned to fear the Lightning's head-on attack, a maneuver possible only because its nose guns could deliver converging fire without the pilot having to guess at range or alignment. The irony was that the idea had not come from the Air Force, or from the ranks of military engineers, but from a quiet civilian with a machinist's intuition. In the bureaucratic machinery of wartime procurement, such figures often vanished into anonymity. But the pilots knew. In the ready rooms of the 475th Fighter Group in New Guinea, where the Lightning reigned supreme, someone had painted a small sign above the gunnery board: "Thank Layton for the kick." The winter of 1943 settled heavily over the American West Coast, but the hangars at Burbank never cooled. Day and night, the Lockheed plant thundered with the rhythm of hammers and rivet guns. Outside, blackout curtains shielded the glow from possible Japanese submarines. Inside, thousands of workers labored in rows that seemed to stretch into infinity. The Lightning was in full production now, its twin booms gleaming beneath floodlights, its armament bays crowded with mechanics adjusting feed chutes and recoil mounts. Edward Layton's work had matured into something far greater than a single improvement. His hydraulic cradle had not only stabilized the 20mm cannon, it had forced Lockheed and the Army Air Forces to rethink how the entire nose battery was integrated. Under his guidance, engineers had redesigned the gun frames to be modular. Armorers could now remove the entire assembly as one unit, test it on the ground, and reinstall it in hours. The change dramatically reduced maintenance time at frontline bases, where dust and heat made even the most precise mechanisms unreliable. By early 1943, the United States Army Air Forces had established a dedicated armament test section at Eglin Field, Florida, to analyze every new weapon system in controlled conditions. Layton traveled there frequently, his civilian badge dangling from a neck strap, his notebooks stuffed with diagrams. He was happiest at the firing range, standing behind blast shields as technicians sent long bursts down range. Each new test produced data: recoil forces, muzzle dispersion, thermal deformation of the barrel clusters, that refined his understanding of how vibration spread through the lightning's narrow nose. One cold morning in February, during a test of a new Hispano M2 cannon, Leighton noticed that after several sustained bursts, the first rounds of each belt tended to wander slightly high before settling into a tight group. The pattern suggested a minute oscillation of the cradle during the first milliseconds of firing, an effect too small to feel but large enough to matter at 500 yards. He returned to his hotel that night and sketched a small hydraulic bypass valve that would release initial pressure more gradually, smoothing the first recoil impulse. Within a week, the modified mount was back at Eglin. The deviation disappeared. For the Army Air Forces, obsessed with standardization, Leighton's meticulous tweaks presented a challenge. Each improvement demanded retooling, new part numbers, and fresh manuals. But Colonel Benjamin Kelsey, one of the P-38 program's earliest champions, understood their value. "This man thinks in microns, and that's why our pilots live in minutes," Kelsey told the procurement board. The colonel's endorsement ensured that Leighton's modifications continued to find their way into production models despite bureaucratic resistance. Meanwhile, reports from combat theaters poured in. In North Africa, P-38's of the 1st Fighter Group were flying long-range escort missions and intercepting German reconnaissance aircraft over the Mediterranean. Pilots reported that their nose guns remained perfectly harmonized even after hours of flight through turbulence. You point, you shoot, you hit. One letter read. Over the Aleutian Islands, where bitter cold froze lubricant solid, the new silicone damping fluid kept the cannons firing. In New Guinea, where humidity corroded everything metallic, the sealed hydraulic lines resisted moisture better than any mechanical spring. Leighton followed these accounts with the fascination of a craftsman watching his tool in use. He had never seen combat, but he could imagine it from the tone of the reports, the relief in the voices of men who trusted their weapons. He wrote to Johnson that summer, "If they don't have to think about the guns, then I've done my part." Johnson's reply was brief but sincere. "You've done more than that. You've given them the punch we promised." As production ramped up, the Lightning's armament bay evolved into a compact ecosystem of precision engineering. The hydraulic recoil cradle anchored the cannon at the center, surrounded by 4 Brownings on rigid mounts. Each weapon had its own ammunition feed, synchronized through flexible steel chutes that coiled like veins through the nose. Armorers developed a ritual for loading: 4 belts of .50 caliber, 1 belt of 20mm shells, all carefully arranged to prevent tangling. When the pilot pressed the trigger on the yoke, all 5 guns fired simultaneously, their streams of tracers merging into a single incandescent line. To enemy pilots, that line was fatal. The concentrated nose battery allowed P-38's to open fire at distances where wing-mounted fighters still relied on luck. One burst from a Lightning could shear off a wing or detonate a bomber's fuel tanks. German crews began referring to it grimly as the Doppelschwanz Teufel, the twin-tailed devil. Japanese aviators nicknamed it Aishikioni, the two-tailed demon. In both languages, the myth grew faster than reality, but the numbers justified the fear. Throughout 1943, Leighton continued to refine his system. He collaborated with ordnance experts at Wright Field to test new types of ammunition: high-explosive incendiary shells with more stable propellants, armor-piercing rounds with tungsten cores. Each new shell altered recoil characteristics, demanding recalibration of the hydraulic dampers. Leighton insisted that every variation be recorded, measured, and compensated for. The result was an armament platform that could adapt to changing ammunition without losing accuracy, a rare trait in wartime engineering. His colleagues often joked that Leighton could hear vibration the way musicians hear pitch. During one test at Lockheed, he stopped a firing sequence halfway through, claiming that something sounded a shade sharp. When they checked the data, one damper valve was indeed running a fraction above its rated pressure. To the pragmatic Californian mechanics, this sensitivity seemed almost mystical. To Leighton, it was simple attention. That summer, he received an invitation to observe gunnery evaluations at the newly formed 20th Fighter Group in England. The Army wanted him to see how his design performed under the strain of European combat conditions. It was his first journey abroad and his first close contact with the men whose lives depended on his invention. At King's Cliff Airfield, he watched P-38's take off into the grey British sky, their twin Allison engines howling in unison. When they returned, streaked with grime and cordite, the pilots described shooting down Messerschmitts at ranges of 600 yards, something previously thought impossible. One of them, a captain with a quiet drawl, shook his hand. "Whoever figured out how to stop that cannon from kicking sideways saved a lot of necks," he said. Leighton only smiled and replied, "I just made it behave itself." By autumn, the Lightning had matured into a balanced and lethal weapon. The combination of long range, climb rate, and devastating nose firepower gave the Allies a flexible fighter unmatched by any other in service. The hydraulic cradle and harmonized gun mounts that Leighton had conceived were now standard on every new aircraft leaving the factory. They were no longer regarded as optional improvements, but as essential features, as much a part of the Lightning's identity as its twin booms. For the German Air Force, which had once dismissed American aircraft as over-engineered curiosities, the shock was profound. Intelligence summaries captured after the war reveal that Luftwaffe analysts were puzzled by the Lightning's stability in head-on attacks. "Its fire seems to originate from a single barrel of great power," one report noted. "We assume a new type of cannon or synchronized firing device." The truth was more mundane and more revolutionary. A civilian engineer had simply figured out how to let physics work rather than fight against it. In December 1943, Leighton returned to Burbank to oversee the introduction of his final wartime refinement, a self-adjusting hydraulic system that compensated for altitude changes. Early cradles had required periodic bleeding of air bubbles, a task difficult at field bases. Leighton devised an automatic equalizer using compressible bladders filled with nitrogen, adapted from aircraft shock absorbers. The new unit functioned flawlessly up to 35,000 feet, making the P-38's guns as reliable in thin air as at sea level. By now he was a familiar figure at the factory, lean, bespectacled, usually in shirt sleeves, forever tapping a pencil against his clipboard. Workers called him Professor Leighton, though he had never taught a class in his life. To them, he was proof that quiet thinking could matter as much as muscle. When the 1000th Lightning rolled off the assembly line in January 1944, Johnson made sure Leighton's name appeared on the commemorative plaque riveted inside the nose section. Small letters among many, but they're all the same. As America's fighter production surged and the war reached its crescendo, Leighton's invention continued its quiet service across every front. Over the Pacific, Lightnings strafed shipping lanes and shredded enemy bombers. Over Europe, they escorted heavy bombers deep into Germany. Everywhere, their precision and stability set them apart. The cannon that once threatened to shake the plane apart now gave it the calmest aim in the sky. For Leighton, the satisfaction was simple. He kept every test report and every letter from the front, stacking them neatly in boxes in his garage. When the war ended, he would return to civilian life without fanfare. But in 1943, as the Lightning's reputation spread, he understood that his idea had become part of something larger, a proof that the boundary between factory and battlefield could vanish when imagination met necessity. By the spring of 1944, the P-38 Lightning was no longer a curiosity. It was a symbol of American air power, an engineering statement as much as a weapon. From the airfields of England to the jungles of New Guinea, the twin-tailed silhouette had become familiar to friend and foe alike. Its long nose, once an experimental puzzle of metal and hydraulics, now housed one of the most refined gun systems in the world. The Lightning could strike fast, hit hard, and, most importantly, hit true. At Lockheed's Burbank plant, the war tempo showed no sign of slowing. The assembly lines ran continuously, producing aircraft that bore the marks of countless refinements. Each new production block incorporated small changes that together made a large difference. Hydraulic seals were improved, recoil buffers recalibrated, and ammunition feeds lined with lighter alloys. Every modification bore the fingerprints of Edward Layton, the civilian engineer whose persistence had turned the Lightning's armament from a liability into a legend. Layton had become something of a folk figure within the armament division. He refused titles, insisting he was just a mechanic who took good notes. Yet everyone understood that his understanding of dynamic recoil and vibration control had set new standards for aircraft gunnery. When engineers discussed new projects, such as turret stabilization on bombers or power-assisted gun mounts, they began with the phrase, "What would Layton do?" His influence reached beyond the P-38, spreading quietly through the entire American aircraft industry. In early 1944, he was seconded to Wright Field, Ohio, to assist the Air Technical Service Command in evaluating next-generation fire control systems. The Army wanted to integrate a new Euro-stabilized gun sight, the K-14, into the P-38's cockpit. Although Layton was not directly responsible for optical equipment, he immediately saw the connection between the sight's precision and the mechanical harmony of the guns themselves. A gun sight could only be as good as the steadiness of the platform behind it. He proposed subtle adjustments to the cradle's damping curve to synchronize perfectly with the oscillation frequency of the aircraft's nose under power. Test pilots reported a 15% improvement in first burst accuracy. The modification was small, but it mattered. When the 20th Fighter Group carried out deep escort missions over Germany that spring, pilots noticed that their first trigger pull now yielded tighter patterns. Lieutenant Jack Ilfrey described the sensation in his logbook. No vibration, no wandering tracers, just a straight red line through the crosshairs. Layton's methodical approach impressed the military engineers at Wright Field, many of whom were career officers unused to civilian informality. He arrived at briefings in rolled-up sleeves, often carrying a box of spare valves and seals to illustrate his points. Yet his clarity won them over. Colonel Albert Boyd, chief of the Flight Test Division, later recalled, "He never talked in abstractions. He talked in thousandths of an inch and pounds per square inch. You could build off his words." While Layton refined the Lightning's gun mounts, the war itself was entering a decisive phase. The Allied invasion of Normandy loomed, and air superiority over Western Europe had become a prerequisite for success. P-38's equipped with drop tanks escorted bombers deeper into enemy territory than ever before. German pilots learned to fear their head-on attack. The concentrated battery of one 20mm cannon and 4.50s could rip through armor plate in seconds. Post-war analysis showed that a P-38's first burst carried more kinetic energy than an entire second of return fire from a Bf-109's twin guns. At Lockheed, Johnson and his engineers continued to push the Lightning's potential. New models, the J and L variants, incorporated turbo superchargers that gave them greater altitude performance. The guns, however, remained nearly identical to Layton's configuration. "If it isn't broken, don't fix it," Johnson told a visiting Army liaison. The only significant change was the replacement of early British-built Hispano cannons with improved American-manufactured versions, a process that Layton oversaw personally to ensure the recoil characteristics matched his hydraulic system. In April 1944, he traveled to the Bell Aircraft plant in Niagara Falls to consult on a similar issue with the P-63 King Cobra, whose nose cannon suffered from vibration problems. The engineers there were struggling with cracked mounts and misaligned belts. Leighton spent 2 days examining the layout, and concluded that the solution lay not in reinforcing the mounts, but in balancing the mass of the feed mechanism. He sketched a counterweight system on a scrap of blueprint paper. By June, Bell engineers had implemented it, and the problem disappeared. His reputation as a quiet fixer grew even larger. Back at Burbank, he continued to correspond with field units. Letters arrived almost weekly from pilots describing their experiences. One, from Captain Thomas Lanfear of the 339th Fighter Squadron, the man who would later share credit for shooting down Admiral Isoroku Yamamoto, thanked Leighton for making the nose behave. The tone was informal, but the gratitude genuine. Lanfear and his wingman, Rex Barber, had used the Lightning's stability to execute a precise deflection shot at the Admiral's Betty bomber, a maneuver that would have been impossible with the unmodified early models. Leighton kept the letter folded in his briefcase for years. It reminded him that even small adjustments in a workshop could change the course of battles thousands of miles away. He never boasted of it. When colleagues mentioned the famous mission, he only said, "The airplane did what it was built to do." As 1944 progressed, the Lightning's reliability made it a natural choice for long-range reconnaissance. Modified F-5 variants, stripped of guns to carry cameras, still used Leighton's stabilized mount frames as structural supports for the nose compartments. The same damping principles that had once absorbed cannon recoil now prevented vibration from blurring aerial photographs. In a quiet irony, the man who had made the Lightning deadlier had also made it a better observer. When the first P-38L rolled out of the factory in mid-1944, its armament system was essentially the final evolution of Leighton's design. Maintenance manuals listed the hydraulic recoil cradle as standard equipment, complete with detailed schematics bearing his initials. The Air Forces adopted the system's key features as the basis for future fighter designs, including the P-80 Shooting Star. Despite his importance, Leighton remained officially classified as a technical consultant, civilian. He drew no military honors and appeared in no press releases. But within Lockheed's engineering circles, he had become legendary. Younger designers sought his advice on everything from hydraulic control valves to stress relief machining. He often repeated a simple maxim: "Don't fight the force, redirect it." That philosophy extended beyond mechanics. He believed that the reason civilian engineers had been able to solve so many wartime problems was precisely because they were civilians. "We weren't bound by procedure," he once told a company newsletter. "If something didn't work, we threw it out. The Army had to write a report. We just got a wrench." By late 1944, Allied air supremacy was nearly absolute. The Lightning, once seen as experimental, was now routine, a workhorse escort and strike fighter. In Europe, it chased retreating Luftwaffe squadrons across the Rhine. In the Pacific, it roamed over endless stretches of ocean, attacking shipping and supporting the island-hopping campaign toward Japan. Everywhere it went, its nose guns spoke with deadly precision. Leighton's hydraulic cradle continued to perform flawlessly. Reports of failure were almost non-existent. Armorers could remove and service the assembly in field conditions using simple tools. Spare parts arrived in compact kits labeled Armament Vibration Unit, P-38. For the Army, this modularity simplified logistics. For Leighton, it was the ultimate validation of his obsession with accessibility. "A design isn't finished," he said, "until a tired mechanic can fix it in the dark." As the war entered its final year, the Air Forces began to look beyond the Lightning toward jet propulsion. The new P-80 promised speeds no propeller fighter could match. Yet even in this transition, Leighton's influence persisted. Early jet prototypes faced the same problems of vibration and gun harmonization, only amplified by higher speeds. Engineers from the Jet Fighter Armament Division studied his damping systems and incorporated similar hydraulics into the new designs. The principles he had developed for the Lightning's cannon became the blueprint for an entire generation of post-war aircraft. Through all this, Leighton remained at his drafting table, content to watch the evolution of machines that bore traces of his ideas. He often said that an engineer's reward was not recognition but replication. If everyone copies your mistake, that's failure. If they copy your solution, that's success. By 1945, his solutions had been copied everywhere. When victory finally came, the Lightning's combat record spoke for itself. It had flown over every major theater, scored thousands of aerial victories, and set transoceanic records for range and reliability. Its firepower was unmatched among Allied fighters. And behind that power lay the steady hand of a civilian who had understood that mastery of machinery began with humility before physics. Leighton returned to Springfield for the first time in 6 years that summer. The war was over. Factories were shifting back to peacetime production. At his old workshop, the same machines that had once turned out cannon parts were now making farm equipment. He stood quietly, running a hand over the smooth steel of a new hydraulic cylinder. The principles were the same, he thought, the purpose different. In the post-war years, historians would credit Lockheed, the Army Air Forces, and Kelly Johnson for the P-38's achievements. Few would remember Edward T. Leighton by name. But the pilots who had fired those perfectly harmonized cannons never forgot the civilian whose idea had made them possible. In their diaries and reunions, they spoke of him simply as the man who made the guns behave. In the months that followed the Allied victory, the industrial landscape of America began to exhale. The tension that had powered factories and design bureaus for 4 relentless years dissolved into a mixture of relief and uncertainty. Airfields that had once echoed with the roar of lightnings preparing for war now lay quiet under the California sun. Rows of decommissioned aircraft sat along the edges of runways, their silver skins dulled by dust and rain. The P-38 had done its work, and so had the men who built it. Edward Leighton was one of the few who remained at Burbank after production ended. Lockheed had shifted rapidly to new projects: jet propulsion, commercial transport, and experimental aerodynamics. Yet the company retained a small core of wartime engineers to analyze what the conflict had taught them. The Army Air Forces requested detailed reports on every component of the Lightning's design: what had worked, what had failed, what lessons could be carried forward. Leighton's section, the Armament Division, was tasked with dissecting the hydraulic recoil cradle that had become standard in thousands of fighters. He approached the assignment with his usual thoroughness. Over several months, he collected maintenance logs, field reports, and laboratory data from around the world. The results astonished even him. Across the entire production run of nearly 10,000 Lightnings, fewer than 200 recorded failures were attributed to the cannon mounting system. Most were minor, seal leaks, cracked fittings, or mishandled valves. Statistically, the cradle was the most reliable subsystem on the aircraft, more dependable even than the engines that powered it. The report's conclusion was succinct: hydraulic recoil isolation constitutes a permanent solution to the problem of vibration-induced dispersion in fixed aircraft armament. For the Air Forces, the phrase permanent solution had a resonance that extended beyond engineering. It symbolized the triumph of methodical civilian problem-solving over wartime improvisation. When the newly created U.S. Air Force published its first engineering digest in 1947, Leighton's cradle appeared in a chapter titled Integration of Civilian Innovation. The editors noted that it had been conceived and perfected outside formal military channels, and had demonstrated the effectiveness of cooperative technical enterprise. In the language of bureaucracy, that was high praise. Lockheed transferred Leighton to its research division, where he found himself surrounded by young engineers fresh from universities funded by the GI Bill. They were eager, brilliant, and, at first, impatient with the lessons of piston-engine days. Jets were the future. Cannons seemed relics. But Leighton insisted that fundamentals never aged. He lectured informally on vibration theory, fluid dynamics, and the importance of mechanical sympathy. "You can't bully machinery," he told them. "You have to listen to it." The phrase became something of a motto within the department. When Lockheed began work on the P-80 Shooting Star, the first American operational jet fighter, the design team invited him to consult on its gun installation. The new aircraft carried 6.50 caliber Brownings in the nose, and early prototypes suffered from severe resonance at high speed. Leighton examined the mounting structure and recognized the same pattern of harmonic coupling he had encountered years earlier in the Lightning. His solution, lightweight hydraulic isolators integrated into the gun bay frame, eliminated the problem. The modification was small, inexpensive, and decisive. Once again, a lesson from the past had guided the future. Meanwhile, the broader aviation world was beginning to absorb what the war had demonstrated, that the boundaries between civilian and military innovation were porous. Universities expanded research in aeronautics. Corporations established permanent liaison offices with the armed services. The government's new RAND Corporation explicitly described its mission as bringing together the civilian intellect and the military requirement. Within this post-war ecosystem, figures like Edward Leighton became prototypes themselves, bridges between two cultures that had once regarded each other with suspicion. In 1948, he traveled to Europe as part of a joint Anglo-American study group on aircraft armament. The group visited former Luftwaffe factories, now silent and repurposed. In one warehouse near Augsburg, Leighton examined the remains of a German experimental fighter fitted with an automatic recoil reduction device strikingly similar to his own cradle. The engineers explained that they had begun development in 1944, but never completed testing. "You were ahead of us by a year," one of them admitted quietly. Leighton nodded, understanding that the race of ideas often ended not with victory, but with survival. The same year, the Berlin airlift began, and Leighton watched from afar as C-54 transports, many designed with Lockheed's input, carried food instead of bombs. For him, the sight had deep symbolism. The hydraulic technology perfected for cannons and landing gear now served to operate cargo doors, flaps, and loading cranes. What had once delivered destruction now sustained a city. "Machines don't care how we use them," he told a colleague. "That's our responsibility." Through the 1950s, he remained with Lockheed, moving gradually from hands-on engineering to advisory roles. The company's focus shifted to high-speed flight and space research, but he continued to preach the same mechanical gospel. When young designers working on the U-2 reconnaissance plane encountered vibration problems in its camera mounts, they consulted him. His advice was characteristically simple. Treat the lens like a cannon, let it move a little, and it will stay steady. The principle worked perfectly. By then, the P-38 itself had become a relic. Most surviving examples were sold for scrap or transferred to museums. Yet, in the new world of jets and rockets, the Lightning's legacy persisted. Every engineer who studied its structure learned something about balance, redundancy, and forgiveness, qualities that were, in large part, Leighton's gift to the design. When the Air Force Museum restored one for display in 1960, technicians discovered that the original hydraulic cradle still operated smoothly after 2 decades of dormancy. They cleaned it, refilled it with fresh fluid, and cycled it by hand. The cannon mount slid back and forth with the same gentle resistance it had shown in 1943. Leighton visited the museum that year as an invited guest. He walked slowly around the polished aircraft, touching the rivets, tracing the seams of the nose panel. When the curator asked him if it looked as he remembered, he smiled faintly. "Better," he said. "Now it's at peace." Retirement came in 1962. He declined offers to write memoirs or appear at air shows, preferring anonymity to celebration. His neighbors in Pasadena knew him only as the quiet man who tinkered with bicycles and built hydraulic jacks for fun. Occasionally, former colleagues would visit, bringing their children to meet the engineer whose invention had steadied the Lightning's guns. He would pour coffee, tell them stories about Kelly Johnson's temper and the smell of gun oil at Eglin, and send them home with advice that always ended the same way: keep listening to the machinery. He died in 1973, a week after his 75th birthday. Lockheed's internal newsletter carried a brief obituary. Edward T. Layton, former research engineer and consultant, contributed significantly to aircraft armament design during World War II. To most readers, the name meant little, but for those who had fired a Lightning, it carried weight. In the years that followed, aviation historians rediscovered his role through archival research. Wartime correspondence, technical drawings, and factory memos revealed his central influence on the P-38's gun system. When the Smithsonian Institution organized an exhibition on American fighter development in the 1980s, curators included a section titled Civilian Ingenuity in Wartime. At its center was a cutaway of the P-38's nose, its 20mm cannon resting on a sleek hydraulic cradle. Beneath it, a small placard read, "Hydraulic Recoil Isolation Mount, developed at Lockheed Aircraft Corporation, 1940–43. Principal Engineer, Edward T. Layton, Civilian Consultant." This innovation eliminated structural vibration and allowed the P-38 Lightning's cannons to achieve unprecedented accuracy. Visitors rarely noticed the plaque's modest wording, but pilots who attended the exhibit lingered over it. One, now white-haired, stood before the display for a long time and whispered, "That's the part that saved me." By the dawn of the 21st century, Layton's story had entered the wider narrative of how civilian creativity had shaped the arsenal of democracy. Scholars pointed out that his work prefigured the modern concept of dual-use technology, innovations that migrate between civilian and military applications. The same hydraulic principles he refined for the P-38 were later used in automotive shock absorbers, industrial presses, and even prosthetic limbs. A line could be drawn, uninterrupted, from the nose of a Lightning over Europe to the suspension of a passenger car on an American highway. And so the legacy endured, quiet and pervasive, like the man himself. When restored, P-38s still fly at air shows. The rhythmic pulse of their cannon echoes a piece of his mind, the precise balance of pressure and motion that he discovered 3 decades earlier in a dimly lit hangar at Burbank. The spectators who watch those planes climb and roll may hear only the thunder of history, but within that sound lies the whisper of a civilian's idea, that force can be mastered by understanding, and that power without control is only noise. Through the last decades of the 20th century, the ripples of Edward Layton's work reached further than even he could have imagined. The P-38's hydraulic cradle, born of a machinist's intuition and a few months of wartime urgency, became a reference point in the design manuals of the aerospace industry. Engineers cited it in discussions of dynamic isolation, the art of allowing force to move instead of letting it tear a structure apart. What had begun as a fix for a trembling cannon had become an approach to engineering itself. When Lockheed merged into the vast web of contractors that built the modern American air and space complex, its archives were sifted by generations of young engineers looking for precedents. They found the wartime memos with Layton's marginal notes, his hand-drawn curves of pressure versus displacement, and the terse instructions written in pencil across the top of a blueprint. Make the metal breathe, not fight. The phrase fascinated them. It captured a philosophy that seemed almost poetic amid the equations of aerodynamics and control theory. In the 1970s, as aerospace firms turned their attention toward reusable spacecraft, A handful of designers at the fledgling NASA contractor network noticed that vibration problems in rocket launchers echoed those of high-caliber aircraft guns. One of them, a young mechanical engineer named Robert Campbell, later recalled visiting the Lockheed Museum and seeing the cutaway of the Lightning's nose. "That was the moment I understood what damping really meant," he said. "Those cannons were little rockets. Leighton had solved our problem 30 years before." Within a year, a variant of his hydraulic isolation system was adapted for the camera mounts on early space shuttles. Meanwhile, historians were beginning to connect his story with a larger pattern: the fusion of civilian and military technology that defined the post-war American century. In 1995, the U.S. Air Force Historical Research Agency published a monograph on the evolution of fixed gun systems. The chapter on World War II devoted 10 dense pages to the P-38's hydraulic cradle, calling it a case study in lateral thinking. The author, Dr. Ernest Gann, wrote, "It is striking that one of the most effective innovations of the air war came not from an ordnance laboratory, but from a civilian engineer who treated a cannon as a machine tool and a fighter as a vibration table." His insight, though mechanical in form, was philosophical in essence. Stability is not achieved by resistance, but by accommodation. That sentence found its way into textbooks and museum panels. Students of engineering began to learn Leighton's name alongside the better-known figures of wartime aeronautics. At the Massachusetts Institute of Technology, a professor of mechanical design used his work as an example of empirical minimalism, doing more with less, refining until only what mattered remained. In 2003, when a restored P-38L named Glacier Girl flew again after 50 years buried in Greenland ice, journalists covering the event rediscovered his contribution. They wrote that the aircraft's guns, still mounted on their original cradle, functioned flawlessly during ground tests. Television commentators mentioned a wartime innovation by a civilian engineer from Massachusetts. Viewers heard the story of how an outsider's idea had changed the design of one of the most famous fighters of the war. For a brief moment, his name returned to public awareness. But the real measure of legacy is not fame, it is continuity. Leighton's principles endured quietly in the mechanical DNA of every machine that followed. The inertial dampers of high-speed trains, the vibration isolators in modern jet engines, even the suspension systems of spacecraft landing modules all carried echoes of that first hydraulic cradle in Burbank. The lineage was indirect but unmistakable, the belief that a structure could stay steady by yielding slightly to the forces that acted upon it. In 2015, on the 75th anniversary of the P-38's first flight, Lockheed Martin organized a commemorative symposium in Palmdale. Among the speakers was Dr. Karen Leighton Morrow, Edward's granddaughter, herself an aerospace engineer. She displayed a faded blueprint from his wartime files, the original sketch of the cradle mount, annotated with his tiny handwriting. "My grandfather never sought recognition," she told the audience, "but he taught me that the smallest part of a machine can change history if it's designed with care." The audience, composed of engineers, veterans, and students, rose in quiet applause. After the symposium, a handful of surviving P-38's performed a formation flypast. As the aircraft banked against the desert sky, the deep rhythmic beat of their engines seemed to carry an older heartbeat beneath it, the thump of hydraulic pistons absorbing recoil, the invisible pulse of an idea that had turned raw power into precision. The sound was both distant and familiar, a mechanical echo of the past speaking to the present. Today, when aviation historians trace the lineage of American air power, they still pause at the story of the Lightning's guns. They note how a civilian from outside the hierarchy of the military-industrial complex changed the way engineers thought about control and stability. They quote the simple logic he left behind in his notebooks: "Force will always find a path. Our job is to guide it." That sentence has outlived the aircraft, the war, and the century that produced them. It remains the quiet creed of those who design machines meant to withstand their own strength. And whenever a restorer primes the hydraulic system of a surviving Lightning and watches the cannon cradle slide smoothly back and forth, they witness not just the motion of metal, but the endurance of an idea, a civilian's gift to a world that once mistook brute power for mastery. The roar of the P-38 has faded into museums and memories, yet the principle that made its cannons so steady continues to hum beneath every wing and wheel that moves by design rather than accident. That, in the end, is the true power of Edward Layton's creation, the quiet, lasting proof that precision, patience, and understanding can make even the fiercest weapons instruments of balance.